Alright, in this video I want to show you how to find the rank of a matrix. I have a 3 by 4 matrix here, and I just want to show you how to find rank. So I'm going to show you in a pretty non-standard way, but this way, the way I do it works, and it's going to be useful for you as well, because it's a slightly different way of the Gaussian reduction, but it's fine anyway. So I don't actually know whether you're familiar with the Gauss-Jordan row reduction, or the Gauss row reduction, but in a nutshell, is an operation which aims to find a better matrix, a matrix, the easiest matrix, a very simple matrix, by taking care um, of the linear dependence between those rows and those values inside the matrix. Um, and this is especially useful if you think about this problem as a linear system of equation, like this. Like I'm pretty sure you have seen this in your first calculus class, like 2x minus y plus 0 z. So plus 2w equals 0, and then negative x plus y plus z plus 3w equals 0, and then like negative 3y negative 2 z negative 4y equals 0. So this is basically a system of equation, but doesn't really make sense in the for finding the rank, so we're just gonna skip it here. I just wanted to make you think about matrices in a slightly different way. We're going to talk about the linear system of the equation another time, and because it's a slightly different topic. But right now we're gonna focus on this. So finding the rank means basically finding. Our aim is to get a 1 here, and a 1 here, and a 1 here on the diagonal, and to get zeros here, here, and here. In order to do that, we can actually exchange, two rows. We can multiply a row for a value, and we can do things like one minus another, or one minus two times the other, like I don't know, the first one minus something like 100 times the second one, and so on. So remember, we can actually do exchange one with the other. So we can exchange, we can multiply, and we can do subtraction between rows. Multiply, I mean, multiply a row by a scalar. By a scalar, I mean a number, because in linear algebra you're gonna hear scalar a lot, and the reason why it's called scalar is pretty interesting, but I'll leave it that for another time. Just think about the scalar as a number. Okay, so let's do this. Let's just do this. So I'm gonna write down my matrix again. Negative 1, 0, 2, negative 1, 1, 1, 3, 0, negative 3, negative 2, negative 4. And remember, we're gonna find the rank of the matrix, and our aim is to get 1 1 1 and a bunch of 0 here. Okay, so we can exchange rows, multiply a row by a scalar, and do subtraction. So the first thing I'm gonna do is to exchange the second one with the first. Okay, so just gonna exchange it, and it's gonna become 1, -1, -1, -3. Oh boy, what I did it. Yeah, I'm sorry, it's just -1 plus plus plus. I don't know why I just copied it with the wrong sign. I'm sorry. Was looking at another example. Okay, so 2 -1 0 2 0 -3 -2 -4. Okay. So I'm sorry about the bubbles. I just exchanged them. So I brought this one up here and this one down here. Okay. So this is something simple. We are actually really allowed to do this. So it's normal. There's nothing wrong in doing it. Okay. So once we're here, I'm gonna multiply because I basically changed the sign because this is actually what I wanted to do. I actually want this one to be positive because it's easier to subtract. So I'm gonna multiply the first by -1. So now I actually gonna change the sign. So it's gonna be 1 -1 -1 -3 2 -1 0 2 0 -3 -2 4. Now I'm gonna basically, the reason why I wanted to multiply is that I wanted to have a positive value here because I like having a 1 here, and the reason why I changed that is that I wanted to have a 1 here. Now that I have a 1 here, my life is still not complete because I wanted to solve this. So I want to have a 0 here. So I'm gonna do the second one minus 2 times the first one. So since you are actually allowed to multiply, we can actually do the second time minus not only one minus the other, but minus 2 times the first one. So this is gonna be fine. So we're gonna basically have this one, minus 2 times the first one. So this is gonna give us let's have it right here. This is actually gonna give us 2 times. So we have the second one minus 2 times the first one, so it's going to be 1 -1 -1 3 and -3. So the first one is going to be the same. We're acting on the second one. It's going to be 0 1 2 8 0 -3 -2 -4. Okay, this is our new matrix. And okay, we have a 0 and we have a 0. We are actually happy, but we're not quite happy because we also want a 0 here. So in order to have a 0 here, we can do, what can we do? Well, let's just have, well, we do have a minus and a plus. We can add on the second one in order to get rid of this one, hopefully. So let's multiply. I'm gonna multiply the second one by -1. So 1, -1, -1, -3, 0, 0 is going to be 0. -1, -2, -8. And then we have 0, -3, -2, -4. Okay. So right now, I'm basically gonna I'm just gonna simplify this a little bit more. I can do the first one minus the second one. First one's minus the second one. I'm just gonna get the 0 here. I just like it, the fact that I was going to get the 0. There's, you know, it's better to have this easier matrix, but our focus should be on getting a 0 here. But it was, you know, a chance. I had the chance to get a 0 here, so I just really want to take it. But this is not the standard way of doing it, of course. So 1, 0, 1, 5, and then we're gonna have the other one which is gonna stay the same, -2, -8, and then 0, -3, -2, -4. Okay, so we're gonna bring our matrix back to positive. So multiply the second by -1. So once I multiply the second by -1, I'm gonna get you know, just the one is gonna stay the same, 1, 5, 0, 1, 2, 8, and 0, -3, -2, -4. Now what I really like will be this one to be 0, and of course in order for this one to be 0, I want these to be positive as well. So next thing I'm gonna do is to just multiply the third one by -1. So the first one is gonna stay the same, second one is gonna stay the same, and the third one is gonna change the sign of all of its values. All right, we're getting there, you know, and this actually gonna be fine. So right now I can just do, you know, the third one minus 3 times the second one. Why 3 times? Well, because I wanna get a 0 here. I don't want this 3 here. I want a 0 here. So I do have a pivot. The one on the diagonal is gonna be called pivot for historical reasons. And I really wanna have a 0 here. So now I'm doing this. I'm gonna have, you know, the first one is gonna be the same. The second one is gonna stay the same, and we're fine with that. I'm gonna have 0, 3 times the second one, so the third minus 3 times the second one is gonna be 0, and we're totally happy. Here we're gonna have -4, and here we're gonna be having -20. Okay, we're kinda happy. We just wanna have a one here, just for completeness. So I'm just gonna do something. Again, we can just multiply this one by, they're also linearly dependent. When I say linearly dependent, I mean that one is dependent on another. So I can just, very easy, I can just multiply the third one by -1/4, -1/4. And by multiplying the third one by -1/4, I'm basically gonna get, so the one is gonna stay the same, 1, 5, 0, 1, 2, 8, 0, 0. I'm gonna have a 1, because I said that we cannot divide, but we can multiply by 1 over, which is like dividing. You might see this as cheating, but it's actually allowed. Only to find the rank, of course. It's not allowed in other methods to find other things, but we're not dealing with the linear system of the equation. We just want to find the rank here, so it's fine. -4, so this is 1, and then we're gonna have 5. So those values here are the pivot. So we basically have pivot equal 3, that's equal 3, column equal 3. So we basically have, by row I mean the linearly independent rows, which are 3, and by column, of course, I mean the linearly independent column, which is also 3, and therefore the rank of this matrix is going to be 3. So if we had, if we have a way to simplify this even further, by, I don't know, subtracting and getting these third pivot, getting rid of this one and so on, and have a bunch of 0 here, and just have the first two rows, then we will be having rank equal 2, but this is not the case. But whenever you have something that it has rank equal 2, and started as a 3 by 3 matrix, or 3 by something matrix like 3 by 4, and so on, it means that the matrices the rows of the matrix are linearly dependent. So for instance, if we have, I don't know, everything multiplied by 2, like 2, 4, and so on, and here we have, I don't know, something else, but everything like multiplied by 2, then they will be linearly dependent, and then we would therefore have a lower rank, because once you have, even if you have, I don't know, the power, all the power of 2, they will be linearly dependent. So that will be pretty easy. So this is basically how you compute the rank of a matrix. It's essentially saying for higher matrices, like, I don't know, a 5 by 5 matrix, stuff like that. It's just gonna take a little bit longer, but this is the way you do it. So remember, the goal here is to have 1, but you don't really have to have 1. Even if you have a 5, would be fine. It's still gonna be counted as a pivot, but I just like to have 1 because it's nice and clean, and but for instance, if you just use normal Gauss row reduction, instead of, I don't know, the Gauss Jordan and so on. You're not actually forced to have one. But if you are I don't know, solving a linear system of equation. But in our case, the goal is to have one is to have a pivot here, and a pivot here, and to have a bunch of zeros here, and you can basically subtract rows, multiply a row by a scalar, and of course exchange them. Like I'm gonna exchange the second with the first one, or the first one with the third one, or the second with the third one, and so on. So this is pretty much it.